This is section 7.1, Solve Linear Systems by Graphing. A system of linear equations consists of two or more linear equations in the same variables. So for example, x plus 2y equals 7 and 3x minus 2y equals 5 would be one example of a system of equations. So together they make the system. A solution of a system of linear equations in two variables is an ordered pair that satisfies each equation in the system. That solution is also the intersection point of the graphs of both linear equations. So to give you a visual, here's two lines that have both been graphed, and their intersection point, 1, 2, is the solution. So remember, that ordered pair stands for x and y. So if we took those numbers and plugged them in for x and y in both equations, it would make both of them true. So, to solve by graphing, step 1 is to graph both equations. So you're going to graph them on the same coordinate grid, and you can do that using slope and y-intercept or x and y-intercepts. So remember, if you put it in slope-intercept form, you can plot the y-intercept and then use slope to find other points, or you can plot the x and y-intercepts to connect that way. Step 2 is to see, do the two lines intersect? And if they do, then that's their solution. The ordered pair of where they intersect is the solution. For step 3, sometimes when you're graphing, especially when you're graphing by hand, it can look like it's at a certain intersection point, but to be sure, you can check your solution by plugging it back into both equations. Okay, so let's do an example. We have y equals x minus 4 and y equals negative 2x plus 2, which are both nicely already in slope-intercept form for us. So to graph the first one, my y-intercept is at negative 4, and then my slope, remember, is actually 1, or 1 over 1. I'm going to go up 1 over 1 to plot more points, and then draw in my line. And then I'm going to do the other line. So this time my y-intercept is at positive 2, and my slope is negative 2, or in other words, negative 2 over 1, which remember could also be 2 over negative 1. So I'm going to count up 2 and left 1, or down 2 and to the right 1. So notice, even as I'm graphing it, I can kind of see where they're going to intersect. So now that I've graphed both of them, I can see the intersection point. Right there. And that falls at positive 2, negative 2. So that means my solution is the ordered pair 2, negative 2. Now, to be sure that that's the solution of this system, I'm going to plug it back into both equations. Okay, so the first one, negative 2 equals 2 minus 4. Well, 2 minus 4 is negative 2. So that one's good. And then for the second one, negative 2 equals negative 2 times 2 plus 2. Negative 2 times 2 is negative 4. And negative 4 plus 2 is negative 2. So let's try another one. This time we have x minus y equals 4 and 4x plus y equals 1. So again, I'm going to graph both of them on my grid, but this time they're not in slope-intercept form. So the first thing I'm going to do is put them both in slope-intercept form. So I have x minus y equals 4. Well, remember, I want to get y by itself. So to do that, I'm actually going to move y over so I don't have to worry about negatives. So I have x equals, and then to get y totally by itself, subtract 4. So I end up with x minus 4 equals y, or y equals x minus 4. So now for my other equation, I have to put it in slope-intercept form. So I'm going to just subtract 4x from both sides. And now I have y equals negative 4x plus 1. So now to graph, start with my first one up here. It has a y-intercept of negative 4. And again, a slope of 1. So up 1 to the right 1, or down 1 to left 1. And my second one has a y-intercept of positive 1 and a slope of negative 4, which remember is the same thing as negative 4 over 1. So I'm going to count down 1, 2, 3, 4 over 1. Or I can go up 1, 2, 3, 4 and to the left 1. So again, as I'm graphing it, you can kind of already see where they're going to intersect. So this time, my intersection right there is at positive 1 and negative 2, negative 3. So I have a solution of 1, negative 3. So actually, I want you to pause the video and plug that back into both equations to make sure that that's the solution. And this last one, I'm going to have you try on your own. So again, if you could pause the video and try that. Alright, so just like with other things we've looked at in algebra, with systems of equations, there's some special cases. So anytime we graph two equations together, 3 different things can happen. So what we've seen so far is when we graph the system, both lines, and they intersect. Right? So then they have exactly one solution. They intersect at exactly one point. The other thing that can happen is that when we graph the line, it actually turns out that that line is the same line. Both lines are the same. So when you end up with the same line, one on top of each other, we say that there are infinitely many solutions. And the last situation is when we graph 2 lines and they are parallel to each other. So if you graph a system where the 2 lines never intersect, well, that means that they have no solution. So again, with parallel lines, here's an example over here for you. They both have a slope of 2 over 1. So algebraically, if 2 lines have the same slope, that should key you in that they're going to be parallel. But if you graph them and they are indeed parallel, again, that means they have no solution because they never intersect. So they're going to have different y-intercepts, but they always have the same slope. And then the last situation we call coinciding lines, when you graph one and then the other one is right on top of it. And since they are the exact same line, they're right on top of each other, that means that they have infinitely many solutions. You could pick any ordered pair that falls on the line, and obviously it would work in both. So that's why it has infinitely many solutions. So, to give you a little practice, we're going to use the graph to determine whether each system has no solution, one solution, or infinitely many solutions. So remember, one solution means it's going to intersect, no solution means they're parallel, and infinitely many solutions means it's the same line. So number 1, y equals negative x plus 5 and y equals x minus 3. That's this line right here and this line right here. Notice they intersect right here at positive 1, 2, 3, 4 and positive 1. So they have a solution of 4, 1. So that means they have exactly one solution, and it's the ordered pair 4, 1. For number 2, y equals negative x plus 5. Again, we're looking at this one. And 2x plus 2y equals negative 8. Well, that's over here. They look like they're parallel. They look like they're never going to intersect. But just to be sure, let's put this one in slope-intercept form to see if they have the same slope. So to do that, I'm going to subtract 2x from both sides. I end up with 2y equals negative 2x minus 8. And then I'm going to divide each term by 2, so I end up with y equals negative x minus 4. And you can see that they both have a slope of negative 1. So they definitely are parallel, which means that they have no solution. For example 3, this time we have 2x plus 2y equals negative 8, this one right here, and y equals negative x minus 4. So actually, you can see that that's the same line, just two different ways of writing it. But to show you that they are actually the same algebraically, remember that this, when we solved for y, also became y equals negative x minus 4. So since it is the same line, that means it's going to have infinitely many solutions. Alright, and number 4, I would like you to try on your own. And that will be it for this section.